So welcome to my talk, Hiding in the Folds. And today we're going to be playing a game of seek and hide with geometry. So I divided this talk into 3 parts based on the old joke that when you give this kind of a talk, the first third should be for everyone, the second third is for the experts, and the last third is for the speaker. So I also get to talk about some things I find exciting. What do I mean with playing a game of seek and hide with geometry? So in the first part, I will define what I mean by geometry, and then we will try to find that geometry. And then I will show how we can hide the geometry again, and that will make the bridge back with the usual matrix vector way of doing things, so you will understand where it was all this time. In the second part, it turns out that in the first part we didn't get everything yet. There will still be some holdouts, some geometric elements that we didn't find. And then I will find those with the invariant decomposition theorem. And in the last part, I will just talk about some quick applications for relativistic physics, and that will end with the Poincare group and a unified Lorentz force law. I should also say that whenever I say geometry in this talk, I'm only going to be talking about flat geometry, so just points, lines, planes, no round things. So let's start our game of seek and hide. First, what is the typical approach to transformations? So ordinarily, for example, when we talked about geometry in the talks we've seen before, typically in computed geometry, you represent a point with homogeneous coordinates, x, y, z, and a 1. For lines, we need 6 coefficients, that's called Plucker coordinates. And for a plane, we have 4 coefficients. It's defined by a linear equation. So we use vectors for all of those. And the same thing is true in physics. When we talk about the location of something, the x-coordinates, it's just a vector x, y, z. Momentum is a vector in the 3 directions. And when we go to relativistic physics, that just gets extended with a time component, right? And for momentum, we get an extra time component of momentum, which is the classical energy. And we also have these things called spinors, which are not vector quantities, but we always represent them with vector quantities, which is very confusing as a young physicist. And I will just give as a, so basically, classically we use vectors to represent everything. That's the point, right? We use vectors. And then if you want to transform something, you need to have some group element which transforms it. So it could be a rotation or a translation, for example. And for each of these different types of object, you need a different matrix representation. So for example, to transform a point, I need a certain representation of the transformation. For a line, I need a different one. And for a plane, I need a different one again. So those are different matrices for the same transformation, right? To move my whole scene to a new place, I still need different matrices. And the systematic approach to this is called representation theory. But there is a first sign of trouble here when we use vectors for everything. And this also relates back to what Steven talked about in his first talk. So if you use vectors to represent everything, so for example, if I take, then I use arrows for everything, pointing at the things I want to represent. So I have an arrow A and B, and I can take the subtraction, right? That's well defined. The sum of 2 vectors is well defined. We have the dot product and the cross product, and all of these things, when you're talking about arrows, are well defined. But when you use them for points, things actually stop making sense, right? Because if I take away the arrows, actually what I was doing is representing points. So then the sum, for example, of a point A and a point B lies somewhere out here for some reason, and the difference lies somewhere else. And if you don't know that everything is actually still attached to this origin here, and that we're actually talking about arrows, then none of these sums and differences make sense. And this goes back to Euclid's first postulate: 2 points determine a single line, and nothing else, right? the result of doing anything with 2 points must lie on the line spanned by those 2 points. So to drive that home, the claim is that for any operation to make geometrical sense, in the case of points, any operation you do on them, a binary operation, should always produce an output on that line defined by the 2 points, because there is no other information. So this suggests a different approach. Instead of using different bags of real numbers and using vectors for everything, we will try to find one bag, and every element in this bag will be something that's geometrically meaningful. And hopefully we will also be able to do this in a way that we are not tied to a specific number of dimensions. Now the teaser is that by the end of this talk, only one of these vector quantities that I talked about will still be a vector by the end of this talk, and all the others will turn out to have been something else. So, first we need to define what I mean by geometry and what properties we want. So we want all operations to work in the subspace of their arguments. And we want to represent both elements and transformations within the same algebra. And instead of using an algebra of arrows, we want to use an algebra built up from reflections, because that turns out to behave the way we need. So there are two key topics I need to cover. That's something we call K-reflections and geometric gauges. So first, the idea of K-reflections, starting in 1D. So if I have a point here, for example, and I reflect this green shape in the point, it ends up being the orange shape over here. And you can see it was a reflection because the head is on the other side. Right? I can also compose two reflections. And then my green shape would first be reflected over P1 to be in the middle here somewhere. And then again to be on the other side of P2. And now you see that the head is again on the same side, so it has really translated. And that's all you can do in 1D. Then when we go to 2D, you get something 9. So my green shape, I reflect it in the line L1, and it ends up being the orange shape over here. I can also then again do two reflections in parallel lines, and then you see that again the green line, green shape is translated into the orange one. And I can also now do something new. I can intersect them at an angle. And now if I reflect first over L1, I end up over here in this intermediary state, and then I reflect over L2, and it ends up being the orange shape over here. And effectively, my green shape has now just rotated around the intersection point of these two reflections, right? So that's another nice thing to have. But now we have a special case, actually, where if you choose these two reflections in lines to be orthogonal, then you would first get the green shape reflected over L1, so it goes to the upper left quadrant here. And then you reflect in L2, so then it ends up here in the lower left quadrant. But that's actually the same as just doing a point reflection, right? And that turns out to be crucial, because that means that actually we will be able to identify a point with those two orthogonal reflections, because they behave the same way. Another key point is the geometric gauges, and that is this idea that if I take my green shape and I reflect it through the first line, it ends up in the intermediary state, and then over the second it ends up in the final state. But all of these rotated versions of that reflection all give the same result. So I don't know which one it was, right? If I just show you the input and the output, there's no way for you to know which particular pair I used. And this is true so long as I keep the intersection point the same and the relative angle between these two lines. And the same is true for translations. So if I take my green shape, I reflect it over the first one, and then back into the orange final state, then no matter which two particular lines I used, you won't be able to tell the difference from the result. So that's a gauge degree of freedom. And that's again true so long as I keep the distance between those two reflections the same and their intersection point, right? And their intersection point in this case is the point at infinity where these two lines meet. Why am I telling you about these geometric gauges? Because they tell us how reflections combine. So if I take my square here and I reflect it 4 times, it turns out that that is actually the same as just doing 2. I'll let that play out again and explain what's going on. So we start with the original shape. I reflect it 4 times. But in each of these intersection points, I have a gauge degree of freedom, right? I could just choose to rotate it differently. And I do that such that one of the reflections from each goes through the other point. And that means I've effectively done the same reflection twice. But doing the same reflection twice is the same as doing nothing. So it drops out. I might as well not have done that one. Right? So I'll just let that play out one more time, because this is a vital point. So again, until it goes through the other one, 2 of them become the same. It cancels, and then it's just a rotation around this new intersection point, which you would have never been able to predict if you just see the original 4, right? So that's a very neat concept. And this is something called the Cartan Dieudonné theorem, and that says that every orthogonal transformation in an n-dimensional embedding space is composed of at most n reflections. So Cartan Dieudonné actually dictates how many reflections can be performed in a given number of dimensions. So if you are in 1D, you can do either a single reflection, you can do 2 reflections, which makes a translation, and then when you go to 3 reflections, that's the same as just doing 1. And in 2D, the same thing happens. You can do a single reflection, you can do 2 reflections, and that now becomes either still a translation or you get something new, the rotation. And then you can compose 3 of them to make a glide reflection. But then when you do 4 reflections, nothing new happens. That's the same as doing 2, as we just saw. And the same thing happens in 3D. Then at the level of 3 reflections, we get something new, the roto reflection. At 4, we get a screw motion. And at 5, we get back 3. So there's nothing new there. And from this idea, we can form our algebra of geometry. So starting in 1D, we want to have points and also point reflections. And we can do 2 of those to make a translation. When you go to 2D, you get something new, the line and the line reflection. But if you compose 2 orthogonal line reflections, as we've seen, that's the same as a point reflection. So that's not something new, and that's actually something I already had. I knew how to deal with points. So everything we had in 1D is now automatically included, because I rediscovered the point in 2D as 2 orthogonal line reflections. And so everything from the row above of 1D is now automatically included. So that's very nice. I do, however, have something new because I have a line. So I can do some new things potentially. So if we explore that, 2 parallel reflections in lines form a translation. If the lines intersect, it is a rotation. That's something new. And if you combine 3 of them, you get a transflexion. And then if you go to 3D, we only get 1 new object again, the plane, and that's it. That's the only new thing. And then if you compose 2 orthogonal plane reflections, you get a line. And 3 orthogonal plane reflections act as a point reflection. So actually, everything I knew about lines is now applicable again, and everything I already know about points is also applicable again. So the only new thing I have is planes. And again, we start exploring what you can do with those. And then again, we find that we can make translations and rotations with planes. We again have the transflexion. And we have something new, that's a rotor reflection. So that's first a rotation, followed or preceded by an orthogonal reflection. And we have something called the screw motion, and that's 2 reflections that make up a rotation, and then 2 orthogonal ones that make a translation that's orthogonal to it. And this flavor of GA is called PGA. And that's our bag of numbers now. Now you're looking at it up to 3D. So just to show you how we work with just this a quick demonstration. So we happen to be in 2D here. So my points are actually the composition of 2 orthogonal lines. And so if you want to take the product, for example, between 2 of these points, then we know already what it should be, right? It should be a translation, because the composition of 2 points was a translation. And we know that that translation should be along the line that is spanned by the 2 points, right? So let's check if this holds. And the secret to checking that it holds is these geometric gauges. So what I can do, of course, is I can rotate each of these freely to pick whichever favorable I want. So I choose it such that the reflection from the red one goes through the blue point. And I do the same for the blue point. until one of those reflections goes through the red point. And then the moment that happens, I've effectively done the same reflection twice, so those two just disappear, and I'm left with two parallel line reflections, which is indeed a translation, and it is the translation along that line, right? So this property now nicely holds. Another key point is then, how do I actually do a transformation? And that's something we call conjugation. And that is this sandwich operator, right? So to actually transform an element y by a transformation x, you have to act on it from both sides by x and x inverse, to be precise. That's a famous thing in group theory, but we can actually understand it again using the geometric gauges. So consider, for example, that I have a point BC, the blue point here, and I want to reflect it in the red line. So how do gauges end up giving the reflection of this point to the other side of the line? So the key thing here is, I should show you, I have drawn two copies of A, but you just couldn't see it yet. So the key insight is that, again, I have everywhere where two reflections touch each other, I have a gauge degree of freedom that I can freely manipulate. So I can freely move around each of these intersection points. Okay. I have to be very careful if I start manipulating them all at the same time. So what is the key insight that I will use now to do the reflection? The key point is that I will take the reflection B and I will rotate it into an A. And I will also rotate C into an A, because then I have two copies of A that touch each other, and that will collapse. And then whatever I'm left over with will be the new point B prime, C prime. So let's see if that works. So the idea is I take the line B and I will rotate it until it becomes A. And then I will rotate C until that also becomes the original A. And at that point, it disappears, and I'm left over with the reflected point here, where now two orthogonal lines intersect. Right? So that's actually explains very nicely how with the geometric gauges you can even explain how composition works. And so that's also why we say that these elements are basically, they double both as the transformation or the element itself. It just depends on if you act from both sides, then it actively becomes a transformation. So now we are ready to find the realization of this geometry. And there are some key observations. So the first one is, as we've talked about now, doing the same reflection twice is the same as doing nothing. So that means that if in this conjugation I act with a reflection R on an element X, and I do that twice, that should be the same as just getting X back. And that means that R, the reflection, should square to either positive or negative 1, right? The sign here doesn't matter. And the key point is that that goes for points, line, and plane reflections all the same way, right? And we know that in a Clifford or a geometric algebra, the products of orthogonal vectors square to scalars. So these are the blades. If you take the product of k different orthogonal vectors, such a quantity will always square to a scalar. And lastly, it is already also a well-known fact that the products of vectors in Clifford algebras make up something called pin groups. And those are indeed the groups of reflections. So we can realize these ideas of geometry that I've talked about now in a geometric algebra. I should still point out that we have to be very careful how we build this up if we are to get our dimension independence. Because remember the equivalence principle from Steven's talk, if you can make it look like a duck, it'll quack. And actually, you might think you're looking at points here now, but you're not, right? These were actually, some of these were perhaps lines. And a key point here is that I start out looking at points here on a line, and when I add only one extra, if I rotate my camera in one extra dimension that suddenly turns out to be there, then what was originally the line that I'm looking at here will stay the center line, right, in this new space. But some of these things which looked like points are actually lines, right? So what was already a line will stay a line. What looked like a point will turn into a line. So that's the principle we have to respect. And so I start with the smallest algebra, R1, 0, 1. And in that algebra, I have vectors and bivectors, and that's it, plus the scalar itself. So the vectors I use now to represent points, and the E0 term, the one that squares the 0, is the point at infinity. And you can mix, and E1 is the point at the origin, and you can mix those two to make any point on the line. But now it turns out that these points I was looking at here in this 1D algebra were actually lines all along, as I just showed, but the line I was already looking at in 1D will remain a line. So what I do is I replace the scalar in the smaller algebra by a new vector, because I have to represent that line now as a vector, because everything that is a vector will become a line now. And so I get a new basis vector E2, right? And now I have all of these lines. And with the lines, I can again start making intersections to build up points. And then if you want to go to 3D, it turns out like, oh, this plane I was looking at the whole time, the two-dimensional plane, that was really a plane, but these lines turned out to have been planes all along, right? I just didn't see it because I was looking at it the wrong way. So again, I play the same game. I have to somehow represent the scalar, which was my plane. I have to start representing that now also by a vector, so that all the vectors are actually planes. And so then you get this algebra, where the vectors now represent planes. You can intersect two planes to make a line, and you can intersect three planes to make a point. And that's how this game works. If you stack it up this way, then everything behaves the correct way, in a dimensional agnostic way. All right, so that's now our realization of this bag of numbers. If I just care about the 1D bag of numbers, let's say, then I choose R01. If I want to include lines, then I have to go one up. And for planes, I have to go to R301. And it's worth noting that this particular view of GA is also referred to as the plane-based view. We've already heard that term in some other talks as well. So this is where I come back to the claim that actually elements of geometry are in general not vectors. Because as we see now, what traditionally we used for the point was a vector, but now we see that for a point we should actually use a trivector, and actually, to be more correct, we should use a pseudo vector. So we start counting from the other side, right? Because that way it will always hold in any number of dimensions. So points are actually pseudo vectors. Lines are pseudo bivectors, right? So you also have to count from the other side. Joining 2 points makes a line. If you formulate it that way, it will work in any number of dimensions. And the plane, that is still a vector, and that will always be a vector. And the same for my physics quantities. So if you are in physics, again, you see that these x coordinates, that's just a point, so that's a pseudo vector. And for the momenta, we will find that that is actually a sum of pseudo bivectors. That's something I'll get back to later. For spinners, I'm actually just going to kick that can down the road to David Eelbode's talk. So he will explain why those are not vectors. But I will still hint at them a couple of times during this talk. So now, the question I want to answer is, where was the geometry hiding all this time? So the first step in hiding this geometry is that we want to go to matrix representations of our Clifford algebra. So what you do, we know that in a Clifford algebra, the basis vectors commute this anti-commutation relationship. That is what defines the Clifford algebra. So EI, EJ plus EJ, EI should be 2 times the metric G. And the metric is a diagonal matrix with P ones on it, Q negative ones, and R zeros. That's just the technical definition of the Clifford algebra. And we wish to construct matrices that respect this same rule. So I want to make matrices, capital E of I, that satisfy exactly the same relationship, but now also I have to replace my 1 by an identity matrix. The way we do this is we start from some 2x2 basis matrices that capture the most essential properties. So I need a 2x2 matrix P that squares to +1, a Q that squares to -1, and an R that squares to 0 in matrix terms. And then you can start building up your matrix representations by taking this Kronecker product of the 2x2 identity matrix, one of the signature matrices, so that's a P, a Q, or an R, depending on which square you want, and then some of these I primes. And all the details to this are actually in the paper, Graded Symmetry Groups, by Stefan and me. And I will now skip over some of the extra stuff you need to do to get these matrices in exactly the preferred order, but the details are in the paper. But now we are ready to start hiding our geometry. So you start with a multivector X, and this multivector has a scalar part, it has a vector part, a bivector part, a trivector, and a pseudo-scalar. And I've separated out every time the part that's origin attached and the part that's at the horizon at infinity. So, for example, for the vector, we have E1, E2, E3, that is a plane through the origin. And then I have the last part, E0, that is the plane at infinity, the horizon. Right? And the same is true for all of these. So that's where this notation comes from. So I have a line through the origin, and I have a line at infinity. I have a point through the origin, which is the origin, and I have a point at infinity. All right, so now if you actually make the matrix representation of this multivector, it looks like this humongous mess, right? But the neat thing about this matrix, so this is a matrix that behaves exactly the same way that our multivectors do, and now just with the matrix product instead of the geometric product. And you notice perhaps that this first column of the matrix is all of the coefficients of our multivector in order with positive signs, right? So I could actually also say that I will represent this multivector with a vector. I just throw away everything else. You just keep this first column that also represents the same information. So what you can do is, instead of saying I have a multivector X and a multivector Y and I want to multiply those, I instead say I take a multivector X and I take a vector that represents Y, right? And so then I can replace my matrix product with a matrix vector product. And that's computationally much more efficient. And then the final step that we need here is I should also take the matrix representation of a rotor, right? Because now I want to rotate, for example, or rotate or translate my multivector X. So in GA language, we have this two-sided conjugation, the sandwich product. And now instead, I want to represent that using these matrix representations. And what's more, I want to represent it as this one-sided product. So I want to find some matrix A, such that if I multiply A on the multivector X, represented as a vector, that it has the same effect as doing the two-sided conjugation. And if you actually work that out, then you find that you get this type of block diagonal matrix. So most of this matrix turns out to be zeros, and just along the diagonal you get some interesting stuff. R is the rotation matrix, and T is a translation vector. So the easiest one to look at here is this block, perhaps. That's the most familiar looking one, perhaps. And so now, because of the fact that it is now block diagonal along the diagonal, we can actually just represent the action of each of these sub-blocks on its relative vector space, right? So I can say, oh, for points, I see now that for the point part, I get this 4x4 covariant representation, as it's called. So to transform a point, I could now take the vector representing the point, act on it with this 4x4 homogeneous matrix, and then I get the updated point. For lines, you have this 6x6 adjoint representation. And for planes, we have a 4x4 contravariant representation. So actually, I can now present a how-to guide for hiding geometry. If you want to hide geometry, you first switch to matrix representations of the multivectors. Then you throw away everything but the first column. You rewrite conjugation into a one-sided matrix product, matrix vector product. And then you recognize this block diagonal structure, right? And you just write each of those blocks down, acting on its own vector space. And then you can make $1 million for big linear algebra. All right, but do you guys hear that? There's still some sniggering somewhere. I think we might have missed someone. Is somebody still hiding? So let's look again at this bivector part. We know that lines have to be the meet of two planes or the join of 2 points, right? That's how you make lines. But if I make a general, if you make a line that way, then the wedge of it with itself should be 0, and that's something called the Plucker condition. But if you make a general bivector B, it will not obey that criterion. And actually, the simple example is if I just take alpha E23 plus beta E01, then if you compute B wedge B, it is not 0. And so that means that if I give you a general bivector, that won't be a line. So it's not an element of geometry. And in fact, it turns out that there are 2 lines hiding within this bivector. And for those familiar with representation theory, this might also seem somewhat strange, because if you take this adjoint representation, so I have the origin attached part of the bivector, so that's a line through the origin, and I have a line at infinity part, and it transforms under this type of a matrix representation. Then if you look in the literature, they will say that such a matrix is reducible, but it is also indecomposable. But we know that can't be right. So hold my beer. Let's decompose it. So that brings me to the second part, finding these last holdouts. So the question is there something beyond Cartan Dieudonné that we might have missed? So first you notice here, if I do a reflection in a single line, so what this illustration shows you is how far a point in the space will move under this action, right? That's what it represents. So a point very far away from the line will move a lot because it has to go all the way to the other side. But a point close to the line doesn't really have to move, and points on the line don't move, right? They stay in place. So that's how you should look at this visualization. So now if I do 2 reflections, then you see that you start to get a rotation around the intersection point, right, as expected. And now you notice what is left invariant now under 2 reflections. That's only this point, right? Everything else has to move around the point, but the point in which these 2 reflections intersect, that's your rotation axis, that remains fixed. But now if I do 3 reflections, something weird happens. Because now I have 3 reflections in these particular lines, and what is left invariant here? If you look at the graph, you do see something appear, right? It does seem like there is a line around here where things don't really seem to move that much, right? So there is still some structure here. And it's neither of the 3 lines I started with. None, I should say. So it is this line, right? That line is still invariant under these 3 reflections. Now, how do I find that line? That is, again, a geometric gauge problem, right? Because I have these 2 lines which are intersecting here from my 2 reflections. So I can actually gauge that, right? I didn't change anything, nothing moved. And now, one of those original lines has become the invariant line, and you see that I still have 2 parallel lines, so there's also a bit of a translation going on. Right? And these things are completely orthogonal to each other, so they actually don't have anything to do with each other. I'll just let that last part play out once more, if it works. Never mind. Oh yeah, there we go. So just by gauging it, I didn't change anything in the plot, and we found the invariant. I can play the same game now with 4 reflections. So that's with a screw motion. So say I have this cube and it undergoes a screw motion, so a corkscrew. That corkscrew can always be decomposed into 2 reflections representing a rotation, and they leave only this one line invariance, right? That's the rotation axis. But if you think about it, that rotation axis is still a one-dimensional subspace, and that whole subspace is left invariant under that rotation. So I can still do things within that subspace, and it won't be manipulated by the rotation. So for example, if I take 2 points now on that line, and I do 2 point reflections in those, then that will still be allowed, and that will give me a translation along the line as well. Right? And if you view it in the full 3D, those 2 point reflections on the line are actually 2 parallel planes. Right? So now I have found 2 intersecting planes that give a line, and then orthogonal to that I can still do 2 plane reflections as well. And the nice thing now is this screw motion turns out to be the product of 2 different commuting bireflections, and it leaves 2 lines invariant, right? So the first one is obvious, that's the rotation axis. But where's the other one? That's the line at infinity, where these 2 planes, the parallel planes, also intersect, right? So you get one line here and one at infinity, and they are orthogonal to each other, and they are the invariants of the screw motion. And that's something known as the Mozzi-Chasles theorem, which states that every rigid body motion can be decomposed into a rotation around, followed or preceded by a translation along a single line, right? And now I want to make this sentence a bit more rigorous and a bit more general to see what's really going on here. A rigid body motion, we now have a new term for that. We would call that a quadreflection, the product of 4 reflections. Followed or preceded, we also have a word for that. That means commuting, right? The order doesn't matter. And rotation or translation, rotation and translation, that means bireflections. So if you want to generalize this phrase a bit, you would say that every quadreflection can be decomposed into commuting bireflections. And now suddenly it doesn't seem to have that much to do with 3D geometry per se anymore. This might also hold, and it does indeed hold, for example, in space-time. So we can actually generalize this idea now, and that's called the invariant decomposition theorem. So every K reflection, every product of K reflections can be decomposed into ceil K over 2 commuting parts. And if done this way, it works for even and odd K in any number of dimensions and with any signature. And we also find closed form exponential and logarithmic functions from this. And these commuting terms that we find here, those will turn out to be elements of geometry again. And so the cool thing is that the invariant decomposition theorem actually says that there is nothing new, there are no new isometries after the bireflections. So in 1D, you can only do 1 reflection or 2 to make a translation. But in 2D, so after you do 1 reflection, you can do 2 reflections to make a rotation or a translation. But then when you do 3 reflections, that's actually the same as doing 2 plus 1. Right? So not 3. 3 is not a new thing. You get 2 and 1. So that would be, for example, in this case, always a translation with a reflection, as we've just seen. And in 3D, it's the same thing. So 3 reflections is actually just 2 plus 1 in an orthogonal space. And 4 reflections, like I showed you with the screw motion, is again 2 orthogonal bireflections. So there's nothing new. If you understand the basic bireflections, you understand everything you need to know about isometries. And so you might be familiar with the famous song ABA by Michael Jackson. ABA, easy as 1 to 1, or simple as do, re, do. Right? So this is a good mnemonic for the fact that nothing new happens after that. So now that brings me to the more formal part about what I mean by invariance exactly. What does it mean to be an invariant of a K reflection? Well, if I define conjugation, just to have a shorthand notation, so conjugation of x by r, I just write that with these square brackets, r acting on x, for shorthand notation. So what do I mean by invariance? Well, if you transform something, it doesn't transform, right? So if I transform x by r, it should go to x. It doesn't change. And you could be a bit more lenient and say, actually, I also accept the fact that it might change sides. So the sides of the plane might turn around, but it's still the same plane. So we also accept that as an invariant. So that leads to a related question. What are the eigen L reflections, x, of R? So you have x, which is itself an L reflection, right? So that's one of our elements of geometry, for example, or another transformation. Which ones are eigen? So that now means they can have any eigenvalue gamma. So that's the more general question to ask. And now we find something really neat. If x is itself also an L reflection, then that means that its norm is a real number. And we know that the transformation R is norm preserving. So that means that if I act with R on the norm of x, so that's x squiggles, that will be the same as x squiggles, right? But I also know from the eigen equation, the eigenvalue equation up here, that it should also be equal to gamma squared the norm. So the norm is both equal to the norm under the transformation, but also to gamma squared the norm. So I find this particular expression, the norm of x should be the same as gamma squared of the norm of x. And so that leads to one obvious conclusion, and that's like, oh, gamma squared must be 1. But there's another solution, and that is what happens if x has a norm of 0. That's also a valid solution here. And the cool thing is that there live the spinners in the null elements with a norm of 0. So I think that's a really deep point to make, and David Ilbode in his talk will go more into that space of solutions. But the cool thing is, I think, if you are going to be a non-trivial eigenelement, so you don't have just a simple plus or negative 1 as eigenvalue, then you have to be null, which is pretty fundamental. But we know already that our elements of geometry, our points, lines, planes, they are typically not null, right? If you square them, it's just usually plus or negative 1 if you normalized everything. Unless they happen to lie on a horizon, right? The points on the horizon or planes on the horizon, they are null. But in general, the ones in our space will have a real norm, a finite norm. So they must be of the type gamma squared is equal to plus 1. And so that means they fall into one of two categories. If gamma is equal to plus 1, then if you work it out, that's equivalent to saying that the element x should commute with R. And you can also have, if I allow for, so those are called orientation preserving, right? The plane, the size of the plane, if it has some hair on it, that keeps pointing the same way. But you can also have orientation inverting. That happens when gamma is negative 1. And then you find that that is equivalent to saying that x should anti-commute with the transformation R. So the simplest example is a reflection itself. A reflection A is the invariant under the reflection by itself, right? Think back to the quiver plot I showed you with all the arrows moving. If you did a single reflection, then that reflection doesn't change. And we also, we say that A is an eigenelement to A, and it characterizes the transformation. Now, it's also worth pointing out that there are also orthogonal vectors, and orthogonal vectors, so an orthogonal vector C, anti-commutes with A, right? We have seen that before in some other talks as well. So if I act with A on C, that gives me negative C. But such an element we started calling ander instead of eigen, meaning other, right? Because it is invariant, but it's invariant because it has nothing to do with it, right? So that's not really eigen because it doesn't characterize the transformation. I cannot reconstruct that transformation if I just know the element C. If I just give you C, there's no way for you to know what the reflection was. And the reason that we needed a new term for this is because there's an infinity of such unhelpful invariants if you go for the dimensional independent mindset. And because there's an infinity of them and they all don't help you characterize the transformation, they don't deserve to be called eigen. Eigen means you characterize the transformation. Okay, so now we go to the next step up, that's the bireflection. So what are the invariants of a bireflection? If I have a bireflection UV, then we know from the famous formula we've seen a lot already, U times V is U dot V plus U wedge V. So that's a scalar quantity and a bivector quantity. And if this transformation is a rotation or a translation or a boost, so a boost is a rotation that mixes a time dimension with a spatial dimension, then these are generated by a bivector. And that bivector is going to be proportional to U wedge V. And such a B always squares to a scalar, lambda, right? And so we can always write those as exponential functions. So if you have such a bireflection, so a rotation, a translation, those are always exponential functions. And this is worth pointing out that actually there's no need for conditional statements of the different cases for rotations, boosts, and translations, because if you say the dot part, U dot V, is the cosine part, and if you just work out that series, you find that that's the cosh function of the square root of B squared. And if B squared is negative, then this corresponds to a rotation. If B squared is 0, it becomes a translation. And if B squared is positive, it's a boost. So if you write it this way, all the cases are covered. And the nice thing is in the special case that you are in the rotation case, then if you work out this square root, it becomes an imaginary number, and that turns the cosh into a cosine. And the same for the sinh, it becomes a sine. And so then it becomes Euler's formula that you might have seen. So this is kind of a generalized Euler's formula that covers all three of these cases. Long story short, the bireflection has two invariants now, right? Because the only invariants under this are the scalar itself and the bivector B, because those commute with this bireflection. And B is now the eigenelement. If I give you, so for example, for a rotation in 3D, then B would be the line, the axis around which you rotate. And so that characterizes it. Once you know that line, you can reproduce it. And for trireflections, we can again play the same game. We can also split them into a commuting reflection and a bireflection. So the reflection is given actually by the vector part of the trireflection. And you can show quite straightforwardly that that commutes with the original trireflection P. And so our trireflection P can always be written as a reflection, small r, times a bireflection, capital R. And the bireflection now is a product AB, right, of two reflections itself. And we already know that a bireflection has an invariant, a bivector B, capital B. So the trireflection as a whole then has three invariants. It has the reflection, it has a bivector B, and the intersection of the reflection with the bivector. Sounds a bit abstract perhaps, but I have a picture here that shows them to you for the 3D case. So the reflection, if you have a rotoreflection, that's the combination of three different reflections. The reflection, small r here, that would be this orange reflection. The bivector is this line, the axis of the rotation. And r times b is the point where this plane and the line intersect. So those are the three invariants. And again, R and B are the eigenelements because they characterize this transformation. And that brings me to the last one. That's the quadreflection, and that's the most interesting case. Because if you take the product of four different reflections, so that's again our screw motion as an example, then we know that each of these bireflections can be written as an exponential function, right? So if I just put parentheses around it, I take the product AB, I know that's an exponential of some bivector B1, and I take C times D, that's the exponential of some other bivector, I call that B2. But now we have a problem because in general, the product of e to the power b1 and e to the power b2 is not the same as e to the power b1 plus b2 unless these two bivectors commute. And for a general pair of bireflections, that will not be the case. So this only happens in the special case that these things happen to be orthogonal. These two pairs of reflections happen to be orthogonal, like I've drawn it here. And yeah, if only there was a principle by which identical mirrors are always eliminated such that we are always left with orthogonal spaces. So it turns out that that is indeed always the case. And so the challenge before us now is to actually find those commuting bivectors b1 and b2. But we know already, hopefully from the basis of the explanation I've given, that that will indeed be the case. Now this is a tough challenge, so maybe we can start doing it the other way around. So a simpler question is, if I have a general bivector, can that be split into commuting parts? So specifically, those commuting parts should all be simple bivectors, so lines in the 3D case. And simple bivectors are always of the form that are always such that they square to a scalar, and they're always the intersection of two planes. So let's start off with the simplest example, and that is I say I have a bivector b, and it's the sum of b1 and b2. And I want to find b1 and b2. And in this case, it's actually quite straightforward. If we assume commutation, we can find the answer very rapidly and then verify that it works. So the way to solve this is I start with this polynomial here. b1 minus bi, b2 minus bi is 0. Because if bi is going to be, at the moments that bi is going to be equal to either b1 or b2, then this will indeed be 0. So I want to find the roots of this, but the b's are bivectors and not normal numbers. So now I just work out the brackets. So I just multiply everything out. And I assume that these things are already commuting. So you find b1, b2 minus bi, b1 plus b2 plus bi squared. And this can be simplified by quite a bit because b1 plus b2, that's just our original b. Bi squared is going to be the scalar value that I call lambda, lambda I. And b1, b2, that is actually the wedge product of b with itself weighed properly. So actually it ends up being this, a half b wedge b minus bi plus lambda I. And from this I can just solve for bi. So that's the equation we find. Bi must be of this form. And I know now, I know my b. So I know almost all terms here except the value for lambda I. And the way to get at the value for lambda I is you take the same equation again and you square it, because then again some of this bi here will become another lambda I if you square everything. So let's do that, and then we find this polynomial equation. It's not perhaps pretty to look at, depending on who you ask, but all of the quantities here are scalars. So this is actually a very easy equation. It just looks a bit complicated perhaps. But each of these quantities is a scalar, so this is just a normal quadratic formula. Right, so now we're back to Charismi. We know how to solve this. So we can just solve for lambda I. If I have lambda I plug it into this formula, and then I know my b's-I. So actually that completes the solution. Again, details, if you want to be more rigorous, are in the paper. So now I can address the original problem. What are the invariant quantities of this quadreflection? So I have the product of 4 reflections, and I want to find these b1 and b2. So we know that the product of 4 reflections will always give a scalar part, a bivector part, and a quadvector part. And so essentially to find b1 and b2, you just take the bivector part of this and you just split it. It's a bivector, so we know how to split it now. And we know that it has to be proportional to this b1 and b2 quantity with some trig functions as coefficients. So essentially, it just boils down to decomposing this part and undoing the trig functions or just normalizing it. And so then we find that for our quad reflection, we have 4 different invariants: the scalar, B1 and B2, which are lines, and then B1, 2, which is where those lines meet. So in this particular example, my B1, one of them would be the axis of rotation, the other one would be the axis of translation, where those 2 parallel planes intersect. And B1 times B2 is a bit hard to imagine because that would live in the 4th dimension. Unfortunately, I don't have a picture of that, but it is an invariant. It's wherever those 2 lines intersect in some sense. So now I can complete this part. We know now that any quad reflection is actually generated by a bivector B, which I can split into 2 parts, a B plus and a B minus. And in the 3D PGA case, this B plus can lie anywhere in space. That's the rotation axis. And B, that should be, wait, sorry. B negative can lie anywhere in the space. So this first one should be a minus sign. So that's the rotation axis, and B plus always lies on the horizon. But in representation theory, we don't split in a part that's anywhere in the space plus a part on the horizon. We split in a part that's attached to the origin and a part that is attached to horizon, right? So we don't have any freedom here in the spatial part. And that is why, if we go back to the story of representation theory, we say, okay, I have my bivector, and I split it into the part that's attached to the origin and the part that's attached to infinity. And then I transform it in this way, and then I say, oh, this matrix cannot be decomposed. But it is because it is the wrong question to ask, because we said it's only things attached to the origin and only things on the horizon, but where's the rest of the space, right? And so that is the mistake that's made there, and that is why this matrix cannot be decomposed. Whereas if we take the GA route, we can decompose it and show that the bivector can always be split into 2 lines. And this is important because this is an often used technique. In physics, we often split a Lorentz transformation into a rotation and a boost part. And in rigid body kinematics, the analogy would be you split a screw motion into a rotation and the translation part, right? So we just make this ansatz that our transformation lambda is of the form translation times rotation, or boost times rotation. And then we find those 2 parts. But the thing is, those are not the correct invariants of the transformation. And so that leads to a lot of non-intuitive phenomenon, and a notable one in physics is Wigner rotations. But that appears because this split is not the correct split to make, because you should split on the invariant quantities, because that's something that all observers can agree on. And then very quickly, we can now extend this actually to general 2K reflections. So this can always be split into commuting bireflections. And a 2K reflection is always generated by a bivector B, capital B, which can then be split into K parts, K commuting parts. And I will just post the formula here. If you're interested, you can look at the paper. But the key point is these wedges of the bivector turn out to be crucial. So you just have to take wedges until this becomes 0. Then you know the value of K, like what the highest one was. So you take these quantities Wm, and then you solve a similar formula to the one we did before. But it admittedly becomes a bit harder. And with this decomposition now, once you have a bivector B and you split it into these commuting parts, then it becomes trivial to exponentiate. Because the exponential of some bivector now just becomes the product of these simple ones, where each of these simple ones essentially follows Euler's formula. So they're all simple. And I could also show you the counterpart of this, which is taking a logarithm. So that's going the other way, given R, find B. I will skip that now, but it is also enabled by this same idea, so we can go both ways. And lastly, something I want to point out is that a 2K reflection. So you take the bivector part, you split it into k different commuting simple bivectors. So that's this first row here, B1, B2, up to BK. But now you can start making combinations of those, right? So you have k choose 2 pairs of these, which are again elements of geometry. So that's all the way up to the last term, and you can start combining them all the way up to the product of all of them, and that will also be an invariant. So in total, for a 2K reflection, you get 2 to the power of k invariants. And those are all valid elements of geometry. And the astute physicist might be thinking, oh, but 2 to the power k invariants in a transformation that acts on a 2k dimensional subspace. That sounds familiar to spinors, because spinors have the same 2k, but then complex dimensional degrees of freedom. And if that is a question you are indeed curious about, then again, I can highly recommend David's talk tomorrow. I just want to quickly address 2 critical questions people might have had during some of the things I said. So one thing you might have noticed is that I need an inverse to do this split, right? So to split a bivector, I had to divide by some complex, complicated quantity. And the question might be like, do you always need that? Because then you've just shifted the problem a bit, right? Because now you need to compute an inverse, which is also hard. But that's not in general necessary. You can also get at it through the eigenvectors of this B. But I think the closed form solution is much nicer to show in a presentation and more insightful. But no, you don't need an inverse. And so far I've only talked about 2K reflections that are of the form, the exponential of a bivector. And a critical person might also say, well, not every 2K reflection is of the exponential form, which is true. But even then, you can show that it is still generated by a bivector. So really, splitting the bivector is all you need. And that is a follow-up paper that we are now working on with Steven and David Ilbode. We don't have the title yet, but that's not the most important part. The most important part is the subtitle. And we do already have that, and that will be Eigen, Ander und Ideal. And the und is there because it's meant to be pronounced in the German way, like Eigen. All right. So that brings me to the last part, which is the speaker part. So now I can briefly talk about what this could potentially yield us in the context of physics. So just as a quick recap, in the traditional everything is a vector mindset, we often think about these Euclidean groups as a semi-direct product of the rotation group and the translation group. Right, so that's SO3 and the translation group in 3D. And then you say any element of the special Euclidean group is a tuple, a pair, of a rotation and a translation vector. And then any arrow in this space transforms as RV plus T. Now, and then in order to transform the higher grade elements, we again need representation theory, as I talked about. Now, as we have seen, in 3D PGA, we got actually a much more elegant representation of these ideas that doesn't need representation anymore. One transformation can act on all the different elements. And a question you might ask is there another famous group that could benefit from a similar treatment? And there is one, and that's the Poincaré group, and that is a pseudo-Euclidean group. And it is the semi-direct product of the orthogonal group in space-time with a translation group. And then we again say that any arrow transforms under a tuple of a Lorentz transformation and a translation. That's an element of this Poincaré group. In the same way, so then an arrow V transforms under lambda V plus T. And again, we need representation theory to work with all the higher grade elements. So that sounds very familiar, and could the PGA mindset give us some advantages here as well? So again, I will start with the 3D algebra now. That was the biggest one we have. And now I need to somehow introduce time. So I will play the same game again, like, oh, I was looking at this space, But actually, it turns out that the planes I was looking at this whole time were really not planes, they were volumes. It was just intersecting my eye the wrong way. So you have that, but you also have the volume itself, and that will remain a volume once you rotate in one extra dimension. So what was planes, what looked to be planes, are going to be volumes, but the volume I could already see will stay a volume. And so I will use an extra basis vector again, E4, to move the volume up to the level of the vectors. So then you get this algebra, 3, 1, 1. And now I have 3 basis vectors squaring to a positive number, 1 squaring to a negative number. And those are volumes. And now again I can start intersecting volumes, 2 intersect into a plane, 3 intersect into a line, and 4 intersect into an event. The nice thing, by the way, about all these elements that we get here now is when you intersect them, when you intersect the spatial parts, you would still get normal rotations. If you intersect 2 parallel, or if you do 2 parallel reflections, you would still get a translation. And you now get this extra thing called a boost, where you mix a dimension of space with a dimension of time. Now, a weird question, or obvious perhaps question you might ask is, why does E4 suddenly have to square to -1? Because we didn't do that before. Well, because it has to. Like, otherwise I wouldn't get space-time. But I cannot give a geometrically tangible answer for why suddenly the square changed compared to the other times I did this. And another question is, why did I choose 3, 1 and not 1, 3? Because in physics that's a common debate. Just the principle of least surprise for this talk. Otherwise, all my pictures and my colors here would have to change. But really, there's no good reason for that. Again, it's probably better actually to do the other one, but everybody's free to choose what they want in that regard. So now we get something nice. We get, for example, that all events are created equal. So any event is the origin plus an amount in the time direction, space, and the different space directions. And so all points are now defined in a homogeneous way. They always have the same square. And the origin is this quantity E1, 2, 3, 4. I have some points at infinity, which are the normal points in those directions. And then I have finally a point at eternity, which is the point to which we're moving in time. And now we can consider something nice. I have a particle at rest at the origin, and it is just sitting there at rest, so it moves towards the point at eternity, right? So the point at eternity is E0, 1, 2, 3. And now I can just join those 2 points together, the origin with the point at eternity. My time direction is upwards. And so now I join those 2 together and I make a line E1, 2, 3. And that is the line along which, the world line along which a particle at rest would move. And so, for example, if I want to talk about a particle now with a mass of m, then in its rest frame, it would move only in the time direction. And so it is represented by this trivector P, which is equal to m times E1, 2, 3. And it squares to negative the mass squared, as we expect. And now this is something that I'm sure Leo will talk about more, the inertial duality. So if I now take the inertial dual map from this momentum line, then you see the symmetry here in this picture, that these momentum generators, or elements, sorry, are dual to the different bivectors. So if I now dualize from E1, 2, 3 here, then I get E4, 0. And if you think about it, so that is the element that generates a translation towards eternity, right? That's my new dimension. That moves me up in space. Up in time. So that's really neat that we get that duality. And now I can ask a question. Which elements do I still have that leave this momentum line invariant? What still commutes with it, in other words? And this is something we technically call the Wigner-Little groups. So the Wigner-Little groups are the invariance groups of a momentum line Pm. And this is exactly the kind of question we had the invariant decomposition for, right? That is exactly the thing that helps us find the commuting subspaces. So if I just do it for this specific particle at rest, where I know exactly that it is proportional to E1 to 3, which elements can I find that leave this invariant, or that commute with it, in other words? So those are these three elements, E014, 024, and 034. But if you take that dual, something interesting happens. Those are E23, E31, and E12, and those are just the generators of a rotation. So indeed, around this momentum line, there's still the invariance of rotation, under rotation. And those are the generators of the spin-free group, which is isomorphic to SU2. And to a physicist, if you hear SU2, you instantly think spin, the quantum property of spin. And so the question is, can I generalize this idea? So if I take now a general pseudo-bivector, P, not for a particle at rest, any one, then I can now always split it with the invariant decomposition into two commuting parts, the massive part and the spin part. So the subscript M here refers to the fact that this part squares to the negative of the mass squared. And it turns out that this PS part, because it's ideal, it lies at the horizon, that always squares to 0. Just like it does, in a sense, in the 3D case. So if I now want to find out what the behavior of this PS is, I do one simple thing. I take PM outside of the brackets. So I'm left with 1 plus PS over PM. And then I have to explore what is this new quantity PS over PM. So I call that S, capital S. And if you investigate, it turns out that's a pure direction. So it's a direction somewhere, pointing somewhere towards space and time at the infinity. And so it has only 4 components. So I can index it with S mu, E mu times the pseudoscalar. So it has only 4 components, not 5 like you might expect. And this quantity S is such that it always commutes with PM. So this S mu is the spin 4 vector. That's the classical terminology for it. And now I can just find PS, if I take its dual, that will be the generators of these Wigner little groups. So if you have, for example, a time-like momentum, like we all are right now, that's the normal case, then you have a spin 3 as an invariance group. So that's isomorphic to SU2 for spin. If you have a light-like trajectory, so like light does, then you find that this invariance group is SE2. And if you have a space-like particle, which are these hypothetical particles called tachyons, then you would find spin 2, 1. And that all follows very nicely from studying these different invariance groups. So those actually, if you just classify this, you find the same results that we traditionally find, but now from the invariant decomposition. And I should stress, by the way, like I'm not making any claims about quantum mechanics. The analysis I'm doing is just purely classical. But I just want to say that these degrees of freedom are clearly present in our algebra. So we're almost there now. Now we get to something called the unified Lorentz force law. And that is the idea that for any k factor x, if you want to see how it updates under electromagnetic fields, so the electromagnetic fields are F, then it always goes via commutation. So the derivative of x is always the commutator product of F with x. And in STAP, our space-time algebra, momenta bylines can always be split into these two commuting parts, as I've shown. And we know that ordinarily for particles, the force velocity is updated under electromagnetic field by something called the Lorentz force law. And the spin is updated by something called the BMT equations. And normally those are two separate problems, and they're treated separately. But maybe our momentum byline has both of those unified, and indeed it does. So actually there's one single unified Lorentz force law that covers both the velocity part and the spin part at the same time. in the classical limit. So where the G constant is 2 and assuming homogeneous field. So that's in the simplest case. But again, I'm not making claims about quantum mechanics. Those are still left to explore. But it's really exciting that the degrees of freedom are already present in this algebra. Okay, that brings me to the conclusions. So starting from some geometrical principles, we first found the pseudo-Euclidean geometry, and that it is captured by Clifford algebras, specifically by the PGAs. And elements of geometry are the invariants of transformations, hence the title Hiding in the Fold. They were hiding in the fold line of the transformations this whole time. And the elements of geometry are also themselves transformations, right? They are interchangeable. And both are represented by K reflections. And we can compose different K reflections with the product, but we've also seen that to act with them, to actually perform a transformation, you use this two-sided product. So X goes to Rx, R inverse. So that's all just the composition of these K reflections under the geometric gauges, with the geometric gauges taking care of the rest. And we've seen that the higher grade K reflections do not give us anything new actually, right? So think do, re, do. There's nothing after re. So nothing after the bireflections. And I hope to have also given a nice preview of how this mindset also has potential for physics, because the geometrical invariants are something that all observers can agree on. And that's a key feature that we like in physics. And the inclusion of the elements at eternity and infinity has also led to a previously unknown unification of the Lorentz force law that includes the spin degrees of freedom. So thank you for your attention.